this video, we will look at how we can relate concepts that we've recently learned concerning the ideal gas law to concepts that we've learned previously that concern reaction stoichiometry. You are by now very familiar with this sort of diagram, which relates the mass of a particular chemical, let's say chemical A, to the mass of a second chemical, let's say chemical B, where they're involved in some sort of chemical reaction. Chemical B could be a product of the reaction. Chemical B could also be another reactant in that chemical reaction. They're related by the fact that we can convert the mass of a chemical to the amount in moles and then relate the two chemicals in amount of moles through the mole ratio. So we've used labels such as needing to use the conversion factor of molar mass to change a mass in grams to the amount of substance. Or if we have the amount of substance of chemical B, we can convert that to the mass using the molar mass. And of course, these amounts of substances are related by the mole ratio based on the stoichiometric coefficient. Now, if we're dealing with gases, we usually need to know other parameters concerning those gases besides just the mass of a gas. Often we know the volume of the gas and we'll know their pressure and temperature. So, in a similar fashion, we can convert the volume of a gas in liters to the amount of substance. Or if we have the amount of substance, we can in turn convert that to the volume of a gas. The way this is done is to look at the ideal gas law and look at the variables that are involved. We, of course, can take the ideal gas law and rearrange to solve for the amount. So if we solve for the amount in moles, we have a new equation that N is equal to Vp over RT. So given the volume of a gas, we can multiply that by the pressure of the gas and then in turn divide by the ideal gas law constant and the temperature. In a similar fashion, we can, using the ideal gas law, and rearrange and this time solve for volume. If we have the amount of substance, we can take that and multiply by the ideal gas law constant and the temperature, and in turn divide by the pressure, and that will allow us to go from the amount of substance to the volume of a gas. These sorts of conversions are therefore similar to what we've done in the past, except we're dealing with different sorts of variables. One of the things to be careful about, however, is do not confuse the volume of a gas with the volume of a solution. Of course, converting between the volume of a solution and the amount of substance requires knowing the concentration of our substance in an aqueous solution, for example. So make sure that you make those sorts of distinctions. It's helpful to look at a couple of examples to show how we can use the ideal gas law relating to reaction stoichiometry. We have a worked out example that involves the detonation of sodium azide and thereby the expansion or inflation of an airbag. Now you might imagine that this could be used, for instance, in inflating airbags in cars when there's an accident. And of course, chemical engineers would want to make sure that they have an appropriate amount of sodium azide. So therefore, the appropriate amount of nitrogen gas will be produced and the appropriate volume will be generated in inflating our airbag in order to save the individual that's involved in the crash. So we have right here the question, what mass in grams of sodium azide must react to inflate an airbag to 70 liters? And we'll deal first of all at STP. So let's break this problem down as we have in the past for typical reaction stoichiometry problems. So of course we always start with our balanced chemical equation and we define what our variables are. That is what we're trying to find out and what information we're actually starting with. So in this case, we have the volume of a gas in liters that we're trying to make. And in a sense, that's our known. And what's our unknown is the mass in grams of the sodium azide that's required to produce that amount of nitrogen gas. Now we're also told that this is happening at STP. So that's standard temperature and pressure. And of course that's 1 bar and 273.15 Kelvin. one thing to keep in mind is that these are not normally ambient conditions, especially in the summer. And so there's a question later on about what happens when the temperature is different. Okay, so volume of nitrogen gas in liters. What we want to do is, in a sense, back convert that to what mass of sodium azide needs to be reacted. Therefore, we'll take that volume of nitrogen gas in liters and convert it to an amount of nitrogen gas in moles. And the sort of conversion factor that we'll need would be then the adaptation of our ideal gas law. So we want to go from volume to the amount. Therefore, given the volume, we'll want to use the pressure and the ideal gas law constant and the temperature to solve for moles. And therefore, we need this version of the ideal gas law equation rearranged. Once we have the amount of nitrogen gas in moles, we can convert that to the amount of sodium azide using the stoichiometric coefficient. And then finally, we can calculate the mass of sodium azide. So you are already familiar with this process, and so I'm going to give you the complete worked out equation right now, but I'll talk you through it. So starting with the 70 liters of nitrogen gas, and what we want to do is convert that to the amount in moles. And so we make use of this sort of conversion factor, which involves multiplying the volume by the pressure, which is 1 bar, because the pressure is at STP, dividing by the ideal gas law constant, and so that's the 0.08314 liters bar mole Kelvin, and then finally multiplying that by the temperature. Of course, that's 273.15 Kelvin. And so all of this is our conversion factor to determine the amount of nitrogen gas in moles. We'll then use the stoichiometric coefficients to convert the amount of nitrogen gas in moles to the amount of sodium azide. And of course, it's 2 moles of sodium azide for every 3 moles of nitrogen gas molecules. Now that after this conversion, we'll have the amount of sodium azide in moles, we'll make use of the molar mass of sodium azide to calculate what mass of sodium azide would be required. And we come up with 134 grams. Now, as I mentioned before, this is all at STP, or 0 degrees Celsius. It'd be interesting to know what mass of sodium azide would be required at a different temperature. And so the key question number 1 asks you to think about how this mass would change if the reaction was conducted at a higher temperature. Now we can do the actual calculation, but sometimes it's easier just to, in a sense, do a thought experiment. So here's our conversion factor for taking the volume of nitrogen gas and converting it to moles. And here's where the temperature will impact the amount that's required to produce a certain volume of gas. And so, for instance, if we increase the temperature and the pressure, the volume, and the ideal gas law constant will all remain constant, what this will do is it will cause the amount or moles that need to be generated to decrease, because we're increasing a variable that's a denominator in this equation. And therefore, if the t gets larger, the n must get smaller. And therefore, we know that the amount of sodium azide that will be required would indeed be less, because we'll need fewer moles, if you will, or a smaller amount of nitrogen gas to be produced. And so smaller amount of gas to be required, smaller mass of sodium azide that will be required. And of course, we could work this out by replacing an exact value of temperature right here for whatever temperature we're interested in. So this is a standard example of how to apply the ideal gas law to reaction stoichiometry. Let's look at a couple of other representative examples. On the next page, you see a question that looks like this. And I would be fascinated to be transported back to around 1783 and to see Jacques Charles try to fill a balloon full of hydrogen gas, and something in the order of 31,000 liters of hydrogen gas. And he would have had to have done this by reacting metallic iron with some sort of acid. And we'll use dilute hydrochloric acid as our example. So you can see a balanced chemical equation for reacting this metallic iron, steel bits, and you would react it with this dilute acid solution and produce hydrogen gas. Of course, also another product would be iron 2 chloride. And of course, he would have had to have worked out, well, just how much iron is he going to be needed to be able to produce this volume of hydrogen gas, and we would have to take into account what temperature and of course what is the atmospheric pressure. And so we have 30 degrees Celsius and 745 millimeters of mercury. This is a typical stoichiometric sort of problem. One of the things, of course, that we are assuming is that the acid in this case, the dilute hydrochloric acid, is in excess. So applying what we generally do to solve a stoichiometric problem, we start with the balanced equation. We define what our variables are. We're trying to determine the mass in kilograms of the iron solid, and we know what volume of gas we're trying to produce. The temperature is 303 Kelvin, so I changed that from the original 30 degrees Celsius. And the pressure we were given was 745 millimeters of mercury. Now, in using the ideal gas law equation, we want to work in bar. So we need to, first of all, change those millimeters of mercury, those units, to kilopascals. Changing into the units of kilopascals is our route to being able to change the units to bar. So you can see that we go 745 millimeters of mercury, use the relationship of kilopascals to millimeters of mercury to find how many kilopascals that corresponds to, and then finally changing kilopascals to bar. And so in the end, we have a pressure of 0.993 bar. What sort of interconversions are we doing here? So volume of hydrogen gas in liters to the amount of hydrogen gas in moles. The conversion factor, of course, involves rearranging the ideal gas law equation. And something actually I should have mentioned before, please do not memorize these conversion factors. You can easily work them out by starting with the ideal gas law, PV is equal to nRT, and rearranging to solve for moles. And once we have the amount of hydrogen gas in moles, we can change that to the amount of iron in moles, and then finally change that to a mass of iron in grams. The overall worked out equation looks like this. And so I will talk you through, but once again, you should be very familiar with these sorts of conversions. So we start with the volume of hydrogen gas in liters. We now have our conversion factor, which involves the pressure of our gas, involves the ideal gas law constant, and involves the temperature. And taking all of this together, multiplying the volume by these gas parameters, we end up with the amount of hydrogen gas in moles. Then using the balanced chemical equation to change the amount of hydrogen to the amount of iron, and it's a 1-to-1 ratio, and then finally the mass of iron using its molar mass. And so we end up with 68,600 grams or 68.6 kilograms. And we're converting this to 3 significant figures as permitted according to our pressure units. Finally, I'd like to talk you through a problem which has some significance in terms of one of the labs that you will be doing. And in that lab, you will be determining the molar volume of a gas, and we assume that that gas is behaving ideally. And the idea here is that in terms of this problem, as well as in the problem that you'll be solving in the lab, is that we need to collect the gas. And collecting gas is a little more tricky than simply doing a reaction in a beaker, because of course the gas can easily escape to the outer environment. And therefore, a common method to trap and collect the gas is to collect that gas by the displacement of water. So you can see here that we have a sample of solid potassium chlorate, and that'll be heated in a test tube, and we'll look at a diagram in a minute, according to this balanced chemical equation. So the decomposition of the solid potassium chlorate results in the production of oxygen gas. The oxygen gas is collected by the displacement of water. And I think it's important for you to know this sort of jargon. And so when you see this in a problem, picture that, yeah, the gas has to be bubbled through water, and we'll actually see a volume of water displaced. And again, I'll refer to a diagram in a minute. Sometimes you'll see the terminology indicate the gas was collected over water. And so that's another way of saying displacement of water. We're given a temperature, we're given a total pressure, we're given a volume of a gas. Now let's take a look. Actually, I should also mention that what we're asked to determine is to calculate the partial pressure of the oxygen gas collected, and then finally the mass of the potassium chlorate that was decomposed. Let's take a look at the diagram here. In the diagram, you can see that I'm representing the potassium chlorate. The magnesium 4 oxide is used as a catalyst, but still we will need to heat the potassium chlorate to initiate the decomposition. Any oxygen gas that's produced will move through this tube and will be bubbled into water. Now originally this inverted cylinder would have been completely filled with water. And the idea is that as the gas is being produced, the level of water will drop. Now we can use markings on this cylinder to be able to determine what volume of gas is collected. One of the things that we need to take into account though is because the oxygen gas is sitting over a body of water, some water molecules will evaporate and also fill this headspace. Therefore, we don't have pure oxygen gas in the headspace, but we also have water vapor. And we need to account for how much water vapor there is. Fortunately, in a sealed container like this, the amount of water that is contained here is actually a constant that depends only on temperature. And therefore, if we know the temperature at which this reaction occurs, or at least the temperature in this headspace, we will be able to determine what we refer to as the vapor pressure of water. And the vapor pressure, as I say, is a constant based on equilibrium principles, and therefore can be looked up in a table. Let's proceed with solving this problem. And what we'll do is we'll lay out our variables so that we can see how to proceed. So once again, starting with a balanced chemical equation, we know the volume of gas that's produced, and we'll use that volume of gas to help us determine what mass in grams of the original solid that had to be decomposed. The volume was 0.650 liters. The temperature, and we'll assume that this is the temperature of the headspace of the gas, was 22 degrees Celsius or 295 Kelvin. So we can come here and look at our table. 22 degrees Celsius corresponds to a vapor pressure of water of 19.8 torr. So this means that this headspace will contain a vapor pressure of water of this 19.8 torr. Therefore, we can determine how much oxygen gas is actually present. And I'll show you how to do this by realizing that the total pressure we're told in this headspace is 754 torr. So a certain fraction of that 754 torr is due to the vapor pressure of water. Therefore, we will subtract the vapor pressure of water, the 19.8, from that 754 torr, and therefore we now have the vapor pressure of oxygen gas alone, 734.2 torr. This is a step that you will always need to take when you're collecting a gas by the displacement of water. Therefore, you'll either be given a table such as this, or you'll be given the actual vapor pressure at the defined temperature. Therefore, the pressure of oxygen gas, and in what I'm showing you here is we'll need to convert that to bar. So the pressure of oxygen gas, starting with the 734.2 torr, we'll convert that to kilopascals, because of course there is the relationship of 101.3 kilopascals per 760 torr. Remember that these are exact relationships and they do not define the number of significant figures. Once we have kilopascals, we can then convert that to bar, 1 bar per 100 kilopascals, and therefore we have a partial pressure, or a pressure of oxygen gas of 0.98, and then only 3 sig figs are permitted, but I'm keeping that extra subscript for calculation purposes, bar. So what's involved in this calculation? So we're going to start with the volume of gas in liters, change that to an amount of oxygen in moles, change that to an amount of potassium chlorate, and then change that to a mass of potassium chlorate. The calculation will look something like this. So volume of oxygen gas, and now here's our conversion factor, which takes that volume of oxygen gas, multiplies it by the pressure, dividing by the ideal gas law constant, and multiplying that by temperature. And all of that, of course, converts the volume of our oxygen gas to the amount of oxygen gas. We then convert the amount of oxygen gas to the amount of potassium chlorate using these conversion factors. Note I say 2 moles of potassium chlorate formula units. That's just because potassium chlorate is an ionic compound, so we really should not be referring to it as molecules. I'm not so picky about that, but I'm trying to use the correct terminology. So 2 moles of potassium chlorate formula units per 3 moles of oxygen gas. And then finally the molar mass of the potassium chlorate to convert to the actual mass of potassium chlorate that's needed to produce that volume of gas. So this ends the examples that we're going through. I think this is representative enough of the sorts of problems that you can expect. Remember that when you're dealing with the ideal gas law, and if you have to use the ideal gas law constant, be sure to make sure that your units of pressure, temperature are consistent with the units of the ideal gas law constant.